So imagine a region of space with a magnetic field that is pointed into the board. And then imagine, if you can, a conducting bar. It could just be a piece of wire, but something that is a conductor and has a lot of free charges in it. And then I want to give it a velocity. So from some external source, we take the bar and we move it into the region of space where there's a magnetic field. So we're just going to be moving it through the space where there's a magnetic field. While it's moving through that space, we know the bar is filled with charged particles. We're going to play like these are positive particles because, like everything else in here, we always follow the motion of positive charge carriers. But we'll play this twice. Once talking about positive charge carriers and what they do, and once with negative charge carriers and what they do. But right now, if you have your right-hand rule ready, and we treat each one of those yellow dots as a positive charge carrier, they're going to experience a force due to the fact that they have all the same velocity, v, as they pass through a region of space with a magnetic field. So what direction would be the force on these charged particles as the bar moves through the field? So all of these charged particles will experience the same size force and will be pushed towards the top of the bar. Now, the size of that force is QVB. Now, what this does, though, is it concentrates charged particles on one end of the bar, making that portion of the bar positively charged. At the same time, it will reveal negative charges that are left standing there. And that will make the bottom end of the bar negatively charged. This is creating an electric field inside the bar in this direction. Now, the forces will pile up until there's enough charged particles to create another force on them. So we want the charges to pile up, but they will stop piling up when the net force on the charges is zero. So as the charged particles pile up and the electric field builds, there'll be another force on the charged particles from the electric field equal to QE. So at this moment, we get QVB equals QE. Now, we've talked about this before for free particles moving through a region of space where we want them to experience no force. That's not what's happening here. These charged particles are concentrated. They are creating this electric field. But by creating this electric field, they're also stopping their own force. So we're concentrating all these positives together. They're all trying to repel each other, but the magnetic field is pushing them together. So that's creating this electric field. Everybody follow along? Now, consider that the size of the bar kind of determines how much of those charges can be concentrated up there at the top. And if you think back to the relationship between potential difference and electric field, you should remember that the potential difference is the electric field times how much they're separated. So if we solve this for electric field, we'll get potential difference divided by the length of the bar. This one is just one of those things to keep in the back of your mind all the time. You tend to forget it. It's a consequence of doing this integration for a uniform electric field. It's one of those things to memorize. So if you ever have electric field, the potential difference is related to the size of the electric field. But what it tells us is how big the potential difference is. We can calculate it. If we cross out the Q's there solve this for potential difference. So I'm using a big V here, and I know there's a little v there. Don't get them confused. You always do. This is for potential difference. We'll get VLB on the other side, where this is the velocity of the bar. Obviously, L is the length of the bar. This is known as motional EMF. In fact, we tend to not write a capital V here. We write that script E for EMF because it's not a potential difference in the traditional sense. We are separating the charges using a magnetic field. They're not being separated due to the action on the charges separately, like in a battery where there's a chemical reaction that liberates the charges. We are moving the charges in the wire to create this EMF. But there's going to be more to it than this. I mean, right now we've just created a potential difference. To use that potential difference, we would need to find a way to channel those charges. It's not particularly hard to do. You just connect a wire from one side of the bar to the other. Provide a pathway for those charged particles to move, maybe give it something for them to move through, some kind of resistance load, and you can have a circuit that is powered by the motion of the bar. Now, this works okay, but doesn't work great. Look at the parameters. If we want a potential difference, we either have to move it fast or have a huge bar that we're pushing sideways to our magnetic field. It's not ideal. And there's a further problem, and I want you to see this further problem. So if we look at that, we just had that big blue wire, that big blue bar. If you're paying pretty close attention, you'll notice that there's a leading edge wire going into that magnetic field. What if it wasn't just a bar? What if I just took and made a triangle wrap of wire, or a square wrap of wire, and I put a resistor somewhere on that wrap of wire. And there's a region of space with a magnetic field. And I just push the leading edge of that wire into the region of space with the magnetic field. So we grab it, start pushing it through there. What happens when both wires are in the magnetic field at the same time? Is it pretty clear that they would cancel out? So this only works as the leading edge goes into the magnetic field or as the trailing end moves through the magnetic field, but not both. So you only get an EMF as you're entering the magnetic field or exiting the magnetic field. Do you see that problem? When both wires are in there, there would be a force on the charged particles on this side of the wire upwards, but there'd also be a force on the charged particles on this side of the wire upwards. And technically there'd be a force on the wire charged particles here, but there's no place for them to go. So the moment both wires are in the magnetic field, you instantly eliminate the EMF that was being produced. But the moment that leading edge of the wire is out of the magnetic field, so the moment that leading edge pops out, suddenly the EMF comes back. But note something important here. The moment that happens, the current in that loop has reverse direction. When we were going into the magnetic field, the current was going to be this way in our loop, right? But the moment we start leaving, the current's going to be this way in our loop. So the direction of the current is going to be based on what part of your wire is entering or leaving the magnetic field. And again, this is known as motional EMF. This alone isn't a great way to create an EMF. It's hard to reproduce this. I mean, how would you do it? Have a wire that you hold one end with a handle and keep pushing it into and out of an area with a magnetic field? That might not be ideal, but it's been done before. I mean, they've created things to generate current that would look like that. using a steam engine and a big wire that's going to be moved in and out of your magnetic field. But you also have to have a magnetic field present for this to work. So permanent magnets, something on that order, something that would maintain a magnetic field. Otherwise, you would need a current from another source to create a magnetic field so that you can create a magnetic field. So you can create an EMF. That makes it tough. Now, there are alternatives to this. There are ways to do this that are different. And that's the work of Faraday. He found that it wasn't just about the leading edge of the wire, that there's something else at play. So Faraday's law is going to take this and kind of run with it and figure out that there are other ways that we can generate this current, ways that are more efficient, but also ways that might be more repeatable. But if you're paying any attention to stuff I've said prior in the year, our wall outlets, they produce a alternating current. That's a sine wave. And so it's passing that current in one direction for half the cycle and the other direction for half the cycle. So you can probably see where that's coming from. Now, it wouldn't be like this, because this would be an instantaneous change from forward to reverse if we push it all the way through the field. So that's not what we're doing to create our EMFs that we have in the walls. We're doing something else, clearly. But this is the start. Which brings me to one side note. This isn't really part of our curriculum, but it's a side note. Permanent. ENT? Like that? Okay, I believe you.